So what we're going to talk about today is the identity matrices. So an identity matrix is denoted by the capital letter I, and it is a square matrix that when multiplied by another matrix equals the same matrix. So if matrix A is an n by n square matrix n by n, and I is an n by n identity matrix, then A times I equals to A, and I times A equals to A. Now, the reason this happens is the identity matrix contains ones along the main diagonal and zeros for the remaining elements. If you were to find the value of the discriminant of both of these, the discriminants would be 1. So basically, if you take A, multiply it by the identity matrix, you're basically multiplying by 1, but you're doing it in matrix format and not just regular 2 times 1 or 4 times 1 format. So you're doing it in matrix formatting. Now, 2 n by n matrices are inverses of each other if and only if their product in both orders is the identity matrix. So if matrix A has an inverse denoted as matrix B, then A times B will equal to that identity matrix 1, 0, 0, 1, and B times A will also equal to that. So if they are true matrices, it does not matter which order you multiply them in, you should get 1, 0, 0, 1 as a 2 by 2 identity matrix. So let's see how this works. So in number 1, we're going to multiply A times B. And we did matrix multiplication earlier. And then we're going to turn around and multiply B times A. All right, of course, I did not leave myself enough room as usual. So to multiply A times B, remember you go across the row of A and down the column. So that would be negative 5 plus 6 for the top number. So we get 1. Then we would have negative 2 plus 2. We get 0. So far, so good. Once I'm done with those numbers, I'm going to use 3 and negative 5. So that would be 15 plus negative 15, which is 0. And then 6 minus 5, which is 1. So according to this multiplication, A times B, they appear to be inverses of each other because their product, the outcome, is the identity matrix 1, 0, 0, 1. Now, if we do this the opposite way, and I'm going to move my matrix A back here because I like to be able to see them in the order that I am multiplying. You don't have to do this if you can keep it in order in your head. Since I am multiplying B times A, I'm going to use this row and then go down the columns of A. So that would be negative 5 plus 6, which is 1. Then I'm going to have 10 plus negative 10, which is 0. So far, so good. Then I'll get negative 3. Once I use that top row, I'm moving to the second row, matrix multiplication. That would be negative 3 plus 3, which is 0. And then I would get 6 plus negative 5, which is 1. So both orders, A times B and B times A, that proves that they are definitely inverses because we get the 1, 0, 0, 1 matrix. Now watch what happens when we try to multiply R times S or S times R. So if we try to prove that R and S are, or determine, I should say, if R and S are inverse matrices of each other, all right, when I start the first one, I'm going to use this row, that column. So that's 48 plus 48. And that does not give me 0. That gives me 96. So I'm going to stop right there because I need a 1 right there. And I don't get a 1 when I do matrix multiplication. So R and S, although they are matrices, they are not inverses of each other because they do not produce the identity matrix. So that's what you're trying to do is you're doing your matrix multiplication to identify whether these are inverses or not. Okay, so the very last problem in that particular set, it does have some fractions in it. So we're going to go through and we're going to multiply C times D. And then we're going to multiply D times C. And we're going to see if the outcome is the identity matrix. Apologize again, run out of room. All right, so C times D, row, column. So that gives me 3/4 plus 1/4, which is 1. Then when I go across the row and down the column, I get 3/16 plus -3/16, which is 0. So far, so good. But don't stop right there because sometimes they try and trick you where the first scenario does give you 1, 0, but the second row is not 0, 1. So keep going. So I'm done here. When I take my -4 and 8, go across that row and down the column for matrix multiplication, we get 1 minus 1, which is 0. And then we get 1/4 plus 3/4 when we multiply -4 times that second column. So we do get 1. So far, so good. So we're just going to turn around and prove it now, because if you multiply C times D and you get the identity matrix, you should be able to multiply D times C and also get the identity matrix. So I'm going to write my C matrix here. You do not have to do this. It's just easier for me to keep things in the pattern and in the flow. So I'm going to use this row and this column, which gives me 3/4 plus 1/4, which is 1. When I use that column and the second row, I get 1/2 plus -1/2, which is 0. I'm done with that column, so I'm going to use the -1/8 and the 3/32. That gives me 3/8 plus -3/8, which is 0. And then for the last set, I get 1/4 plus 3/4. That's what I get when I multiply these two numbers down this column, okay? And that gives me a 1. So yes, C and D are inverses with respect to each other because when you multiply them together, you got the identity matrix. Now, the last thing in this particular section that we are going to do is we're going to determine if something has an inverse, okay? Not all matrices have inverses. So matrix A does not have an inverse if the determinant remember, those are not absolute values. That's just symbol for the determinant equals 0. Now, if you do the determinant and you get anything other than 0, you have an inverse. Okay, so not all matrices have inverses. So how you calculate this, if you have matrix A, which is a 2 by 2, and you want to find the inverse, notice these 4 elements have switched. A lot of things have changed. So what you're going to do is you're basically going to say the inverse is 1 over the determinant, not the absolute value of the determinant. A determinant can be negative, and that's okay. And then notice that you have switched things around. A and D have switched places. And then C and B, you just change the signs. You don't necessarily make them negative. If they're already negative, they change to positive. If they're originally positive, you will change the sign to a negative. Okay? So as we go through, watch the pattern because it is a set pattern. And that's one of the things I do like about matrices is because it does have a lot of patterns to it. All right. So in the first one, the first thing I'm going to do is find the determinant. So I'm going to define the determinant of A, and I'm going to multiply 4 times 3, and I'm going to subtract -1 times -6. That gives me 12 minus 6, which is 6. Since my determinant is not 0, I am going to keep going. If my determinant was 0, I would stop and I would say that the inverse does not exist. So I'm going to keep going. I'm going to find the inverse of matrix A. That is 1 over the determinant. Now, I am going to, that 1 over the determinant becomes a scalar. All right. And now I'm going to follow the pattern. These two numbers switch places. So 3 and 4 switch places. And then what I'm going to do is I'm going to change the signs on these two numbers. So 1 and 6. You don't move them. Whatever they are, you change their signs. So now I'm going to have 1 over 6. I apologize. I'm not going to have 1 over 6. I'm going to distribute 1 over 6. So that would become the inverse matrix. The inverse 2 by 2 matrix would be 1/2, 1 over 6. And I don't know why I did that out of order because I usually do row first and then column. So if you take your 1 over 6 and you distribute it throughout the matrix, this is your inverse matrix. Now, what happens is if this is truly the inverse, if you take matrix A and you multiply it by the inverse, you should get the identity matrix 1, 0, 0, 1. That's what inverses are. Now, in number 5, the first thing I always do, and I suggest you do it too, is you find the determinant. So that would be 8 times -1 minus -4 times 2. So that's -8 plus 8, which is 0. So there is no inverse for this problem because the determinant is 0 and you can't have 1 over 0. You cannot have 1 over 0. So not everything has an inverse. All right, so find your determinant first. If it's not a 0, keep going. If it is a 0, then you need to stop. All right, the last few problems we're going to do. First thing I'm going to do is I'm going to find the determinant of this matrix that they give me. So that would be 40, 8 times 5, minus -80, which is 120. So in order to calculate my inverse, I have 1 over the determinant times, now I have to switch things around. 8 and 5 switch, so that would be 5 and 8. And then I change the sign, so that's +10, -8. And then I distribute my 120. So the inverse for the given matrix is 1 over 24, 1 over 12 when you distribute that scalar, 1 over 20. And then on the bottom row, I get -1/15 and 1/15 on the bottom row. This is the inverse for the given matrix. For number 7, we're going to find the determinant first. That would be -18 minus -18 minus -24, which gives me +6. So to calculate my inverse, I get 1 over 6 because I can keep going because my determinant was not negative. Then I'm going to switch things around. Negative 6 and 3. And then I have these two. You do not move, you just change their signs. Distribute, and you get negative 1 and 4/3, top row. Bottom row, you get negative 1/2 and 1/2. And that would be your inverse. For number 8, I'm going to find my determinant first, which would be positive 12 minus 12, which is 0. So no inverse exists. And then for the last example, for the set of inverses, we have the determinant, which is positive 30 minus negative 90, which again is 120. That's kind of weird that I had 2 with 120 in it. So we're going to take our inverse, 1 over the determinant, which is 120. We're going to switch the 5 and the 6, so negative 6 and negative 5. Then we change the signs. That would be positive 9, negative 10. You distribute your 120 all the way across, so that's negative 1 over 20 in the top row, 3 over 40. Bottom row is negative 1 over 12 and negative 1 over 24. That would be your inverse for the given matrix for that particular problem. So if you have any questions, please let me know. We should be starting. I do need you to go ahead and fill out these notes. I don't think it is impossible for you to do without my assistance. That way we can jump straight into Kramer's rule when I get back. So let me know if you have any questions or concerns.